We are now going to start talking about electric current. And as I think I previously said in previous lectures, when we studied static electricity, we were studying the effect of charged particles that were not in motion. Electric current, by definition, is charged particles that are moving. And that's what we'll be talking about this time. So electric current is the rate in which the charge flows within a conductor. In this situation, what we have is I, which is the symbol for current, is equal to the change in charge, Q, over the change in time, T. I is frequently is the SI unit ampere, and that represents a coulomb, coulomb being a unit of charge and second being a unit of time. And so when we talk about amperes of current, we're talking about the amount of charge that travels past a certain point in a conductor over a period of time, a specific period of time. So here's a diagram that shows the motion of charge. It shows it traveling through a cross-sectional area of a conductor, and the current here represents the flow rate. And if you assume that this circle that we see here is the point that you're talking about, the flow of charge across that circle is the current across that circle. So if we're talking about this, it says, what is the current involved when a truck battery sets into motion 720 coulombs in 4 seconds when starting an engine? And as we said, it's the change in current, which in this case is 720 coulombs, over the time, which in this case is 4 seconds. So it's essentially 720 divided by 4. And if you do the math there, you'll see that that's 180 amperes. How long does it take for 1 coulomb of charge to flow through a handheld calculator if the current is 0.3 milliamps, which is 10 to the minus 3 amps? Now again, we know that I is equal to delta Q over delta T. So delta T, if you solve for delta T, that's going to be delta Q over I. So in this case, the time period would be 1 coulomb divided by 0.3 times 10 to the minus 3, or 3 times 10 to the minus 4. Again, if you do this, the math there, you'll get 3,333 seconds. A circuit is a path in which the electrons can travel, or the current can travel. A simple electrical circuit is a closed path that current flows through and is supplied by conducting wires, and it connects to the two sides of the terminal of a battery. The diagram A shows what things look like in real life, and diagram B shows the way you would write this out schematically. You can see that the battery is the power source, and here it is represented by two parallel lines, one of which is longer than the other. And when you draw it in this way, the longer side represents the positive terminal of the battery, and the shorter side represents the shorter, or the negative terminal of the battery. So this, and also notice that the flow is always from positive to negative. The direction of flow is always from positive to negative. Now it's convention to talk about the flow as the direction in which a positive charge would flow, although positive and negative and both are actually flowing. One's flowing in one direction and one's flowing in the other direction. You know that the positive here would go from the positive side to the negative side because opposites attract. At the same time, the electrons are actually going in the opposite direction. By the way, I wanted to mention the squiggly line at the top of the diagram represents the resistance or the load or the device that's being powered by the battery. And in this case, it's the headlight in the top diagram. Current, I, is the rate in which charge moves through an area, which is represented as A here. The conventional current is defined to move in the direction of the electrical field. So the field moves from left to right. The positive charges move from left to right in the same direction as the field moves. The negative charges at the same time are moving in the opposite direction. This is all convention, and it's basically somebody a long time ago decided to do it this way. And the flow of electrons, which is sometimes referred to as electronic flow, is always in the opposite direction of the field. The positive charges move in the same direction in the field, and you can see the I represents the current, and the current is always the same direction as the direction that the positive charges would flow. So if you have a 0.3 milliamp current, as in the prior example, how many electrons per second would pass through it? So the way that you would do this is to understand that 1 coulomb of charge is equal to 1.609 times 10 to the 9th electrons, or 10 to the 9th positive charges. And so you would take that 1.609 times 10 to the 19 and divide that by 3,333. And if you did that math, you'd get 4.8 times 10 to the 15th electrons that pass through that little disk marked by A every second. This shows that when the charged particles are forced to move into a particular portion of the conductor, an equal number have to move out. So if you look at the left, you'll see that the electron is moving into the section of the conductor that we're looking at here. At the same time, one has to leave at the same moment, because you cannot build up electrical charges in a conductor. The repulsion between the like charges makes it difficult or impossible to increase the number of charges per volume. And so as one charge leaves or enters, another charge has to immediately leave. And conductors work the way they do because the charges are free to do this. When you have an insulator, insulators bind their charges to the atoms inside, and charges can't move. And therefore, since charges can't move out of the insulator, charges can't move in. And that's why insulators work the way they do. Now this shows the actual path that electron actually has to take in terms of its motion. So although we visualize it as something that moves straight through the conductor, the fact is that it moves in a very haphazard and wild way across the conductor as it's moving from the left side to the right side. And as you see, it's in the opposite direction of the field and the opposite direction of the current. Free atoms move in a conductor, and they make collisions with other electrons and with other atoms. That's why this haphazardness occurs. This is the path that's shown here. The average velocity that an electron moves through the conductor is called the drift velocity, or v, and that's supposed to be subscript d. And it is in the direction opposite the field. The collisions transfer energy to the conductor, and therefore there's a constant energy required to keep the electron moving at a steady state. A good electrical conductor is commonly also a good heat conductor. This is because there's a lot of free electrons, as I said before, and those free electrons allow motion both of electrons into and out of the conductor, and this also allows the heat, the increased energy that occurs with heat and the increased motion that occurs with heat, to move through the material very quickly. Now let's look at how we can actually conduct or calculate this drift velocity. All the charges in the shaded volume move in and out during time t, and they all have a drift velocity of v subscript d. And so the velocity that they move is the distance x, which is from one of the circles on the left to the dashed circle on the right. So in that time, the charges move through that distance x over a period of time t, and so the drift velocity is equal to x times t. Now we know that current is equal to the change in charge over time. And you can express this current, or charge, as the quantity of the charge of the particle times the number of free charges in that volume times the cross-sectional area of that volume. And that's represented, Q represents the charge of the particle that's moving, N is the total number of Q's in that volume, and A sub X is the cross-sectional area. And so I then, if this is true, if delta Q can be expressed this way, then I is going to equal NQA times the drift velocity, substituting VD for X over T. So let's do a calculation, and I'm going to actually do this so you can see the calculation being done because it's a little bit more complex. Let's do a calculation of a drift velocity for electrons in a 12 gauge copper wire whose diameter is 2.053 millimeters, carrying a current of 20 amps. There's one free charge per copper atom, and the density of copper is 8.8 times 10 to the third kilograms per meters cubed. And I'll show you why you need all this information in order to do this problem. First of all, we know that I is equal to NQA VD. Okay, and we have to figure out N. We know Q because there's one charge per copper atom, so Q is 1. A is going to be pi r squared, which r is going to be 1/2 of d. And VD is what we're trying to calculate here. We know that I is equal to 20 amps. So the big question here is, how do you do N, okay? And as it turns out, the number of particles in the volume is going to equal to 6.023 times 10 to the 23rd. We know that's 1 mole of particles, times 1 mole weighs 63.54 grams for copper, times there's 1,000 grams in a kilogram, and that's just because we need to be working in kilograms in order to use the density, which was 8,800, or 8.8 times 10 to the third kilograms per meter squared, cubed, So if you multiply all this out, you see this cancels this, and this cancels this, and this cancels this, and you end up with the number of particles per cubic meter. And so that doing the math here, you get 8.342 times 10 to the 28 particles or atoms or electrons, however you want to say it, per meter cubed. Okay? Now, we can put this number with the rest of these. First of all, let's solve this for VD. VD is going to equal I divided by NQA. Let's go ahead and calculate A here. A is pi r squared, which is going to be pi times, it's 0.00106 squared. So A ends up being 3.31 times 10 to the minus 6 meters squared. So now we can say that VD is equal to 20.0 divided by 8.342 times 10 to the 28 times Q, which is 1, times A, which is 3.31 times 10 to the minus 6. And if you do the math here, I'm sorry, this one charge is actually 1.609 times 10 to the minus 19. It's one charge, but this is going to be 1.609 times 10 to the minus 19. And you put this in here, do all the math here, and VD is equal to 4.53 times 10 to the minus 4 meters per second.